Thanks for Judy for the talk. So our next speaker will be Cihang Xie. So Cihang is an assistant professor of computer science and engineering at University of California, Santa Cruz. His research interest lies in computer vision and machine learning, intending to build human-level computer vision systems, particularly in securing model performance under the worst-case scenario and enduring models with interpretability. He received the Facebook Fellowship in 2020. So the talk title is Adversarial Example Improves Image Recognition. So let's welcome Cihang to give the talk.
Okay, thanks for the introduction. Just give me 1 minute to set up those slides. Let me see. Okay, cool. So, as mentioned, like in a lot of previous works, adversarial examples generally are treated as threats to deep networks, right? And a lot of previous efforts on this direction is trying to say, okay, how can we build more robust models and make these models to get rid of adversarial examples? While in this talk, I will try to bring some different things to you guys. Specifically, in this talk, I will try to show how can we use adversarial examples to help your deep networks. For example, like suppose you get your networks with adversarial trained, your network will have, say, better in-domain and the out-of-domain generalization ability. So first, let's talk about the motivation. Before our work, there are indeed a lot of works showing that adversarial trained models indeed get some valuable and new features. Okay. So for example, in this loss gradient visualization, where like the people just do the loss gradient with respect to the input pixels. The second column row here, you can see is a visualization from the vanilla trained models. You can see basically like these patterns are completely noisy and a human cannot see any patterns here, right? But for the third column, third row here, that's the visualization for the adversarial trained models. You can see these visualizations are highly human aligned, which means the adversarial learned models and vanilla learned models are indeed learn some different features. And in the other points that this adversarial learned features are more aligned to human perception. And also people are showing that adversarial trained models are pretty good at tackle image synthesis task. So given these two works, there's also another dilemma here, is that when you use features exclusively from adversarial examples, they usually degrade your model performance. And here you can see we train two models, B3 and B7. Currently, like you do not need to know like what is B3 and what is B7, and which I will detail it later. But you just need to remember that B3 is a small model and B7 is a large model. The blue bar indicates this model is vanilla trained, which means you just apply some clean images, do the training, and this gray bar are adversarial trained. And the y-axis is the ImageNet top-one accuracy. You can see that compared to the blue bar, the gray bar has significantly lower accuracy when testing on the ImageNet validation data sets. This indicates that training exclusively on adversarial examples will significantly degrade the performance on clean images. And one hypothesis we try to explain this phenomenon is that probably adversarial examples and the clean images, they came from two different distributions. Okay, so that's why you train on the adversarial examples and then test on clean images. That cannot generalize pretty well, which causes this significant performance degrade, right? So to validate this hypothesis, what we do next is we take these adversarial trained models, we then fine-tuning these models with clean samples. So this step can kind of simply bridge the domain gap, right? Because you first train with adversarial, and then you fine-tune with clean images. And then the results is shown in this orange bar. You can see that compared to this gray bar, this result gets significantly improved, which kind of can validate our hypothesis about the distribution mismatch between the adversarial examples and clean examples. And furthermore, when we compare this first pre-train on the adversarial and then fine-tuning on the clean images to the popular vanilla baseline that's only trained with clean images, you can find that for B3 model, these two performances are already pretty close. And for B7 model, which is a larger model, you can see this green orange bar can even outperform this blue bar here. So given these results, and also what we just applied for the orange bar is a very, very simple algorithm. The next question is, can we design some more sophisticated algorithms to further improve the model performance if we utilize adversarial examples? So let's bring our solution called adversarial propagation. The key point in our adversarial propagation is we should do joint training, but with distinguishing. For the joint training, recall that in the previous pipeline, we first pre-train on this adversarial images and then fine-tuning on these clean images. But this first pre-train and then fine-tune paradigm may cause some catastrophic forgetting issues, right? Because you later train on some clean images, probably you forget some useful features that you learned from adversarial images. So a better choice is that we should train with adversarial examples and clean images at the same time. And this is proposed by Ian Goodfellow in 2015 about the adversarial training algorithms. This is something not new, right? But for our contribution in this solution is when we do the joint training, we should care about the distribution mismatch. The main reason that we should care about this problem is that in this training framework, the network usually contains a block called batch normalization layers. And for the batch normalization layers, the basic function is that it takes the inputs and calculates a single mean and a single variance over this batch, and then apply this mean and variance to normalize your input features. So this is a milestone in the deep learning history because it can accelerate your training and also make your training much more stable. But in this joint adversarial training case, the BN layer will cause some problems because, as we mentioned before, we think adversarial examples and clean images, they came from two different distributions. So if you just naively apply the batch normalization layer over this mixture of distributions, you will cause some confusions, right? As illustrated here. Originally, you should estimate like 2 mean and 2 variance for adversarial distribution and clean distribution respectively. But here you just do the mixture one, right? So the statistic estimation at the batch normalization layers will be confused while facing this mixture case. So our solution, again, is pretty simple. What we do is we add an auxiliary batch normalization layers. So that means for the mixture of inputs only at the batch normalization layers, the clean images will go through the main batch normalization layer, and the adversarial images will go through these auxiliary BN layers. So such design can guarantee that the data from different distributions are normalized separately. And basically, just as illustrated in this figure, you can say by this simple design, you can again, get the right statistic from clean images and the adversarial images with the right statistic. And at the test time, our adversarial propagation, because you have 2 batch normalization, right? One is the main BN you get from the clean images, and one is the auxiliary BN you get from adversarial images. And for simplicity, at the inference time, we just drop this auxiliary BN, and only the main BN, which is obtained from your clean images for the inference. Before we go to the experiment session, I want to give you a brief background of the network we use called EfficientNet in our experiments. So before EfficientNet, people knows that for a baseline network, if you make this network be wider or deeper, or your input get larger resolution, you will get better performance. And EfficientNet is just take a step further. It say, okay, if you already know, simply go through the deeper, wider, and the larger resolution can improve. Why not do this scaling, these three factors at the same time? And they call this factor as compound scaling, and use the neural architecture search techniques to search the right factor for scaling these three parameters. And basically with EfficientNet, at least in 2020, this is the best architecture on getting the state-of-art performance on the ImageNet dataset. So the x-axis is the flops, and the y-axis is the ImageNet top one accuracy on the validation dataset. You can see basically for the EfficientNet B0, that means it's a very small EfficientNet, which can run on your mobile device. And the B7 here is a very large EfficientNet model. As a side note, EfficientNet B7's 84.5 top one accuracy on ImageNet is the purest state of art on the ImageNet classification data task. So by building upon this already pretty strong baseline, our ADU prop can consistently improve the baseline model. For example, like on small models like B0, we can get 0.3 improvement. And for B5 and B6, you can get a 0.6, right? And for this already like very big and the pure state-of-art B7 model, our model can again give some additional performance gain. It can further improve the performance to 85.2, which is again like the state-of-art performance on ImageNet classification. And if we just solely look at this ImageNet in-domain generalization performance, you probably think, okay, this like your method, the benefit bring by your method is kind of pretty small, like say 0.3 improvement, 0.7 improvement. So to further support the effectiveness or the power of our method, we also do some out-of-distribution generalization tests. The first test that we performed is on the ImageNet-C dataset. The purpose of this ImageNet-C dataset is to benchmark the model's robustness against different image corruptions. For example, your image may go through some blur, the JPEG compression, and give this new images for testing the robustness. And the second dataset we choose here is called ImageNet-A dataset. Basically, ImageNet-A dataset is a collection of some very hard natural real-world images. For example, the true label of this image is actually a bird, but you can see the bird is pretty small here, right? Which is even very challenging for our human observer to recognize this image. And the third dataset is called stylized ImageNet. Basically, this dataset is removing all the texture patterns, and the purpose here is to benchmark the model's shape representation power for recognizing these images. So for the original EfficientNet B7 models, when we test on those three different data sets, on ImageNet-C, we got a 53.1 accuracy. On ImageNet-A, we got a 37.7 accuracy. And on stylized ImageNet, we got a 28.8 accuracy. And do you recall that on the original ImageNet, EfficientNet B7 got 84.5 top one accuracy. So that's a huge drop on this data set. and also demonstrate this task is extremely non-trivial. And by adding adversarial propagation, we can see that on ImgC dataset, our accuracy, we can improve the accuracy by 5.1 top one accuracy. And on the ImgA, our improvement is 7%. And on the stylized ImgNet, our improvement is 4.8 improvements. And again, as a side note, the very popular ResNet 50 baseline here, you can see it only got 40.7 on the ImgC dataset, 3.1 on the ImgA dataset, and 8 point on the stylized ImgNet. So if you just look at the absolute value here, you can see this is a huge improvement over the existing methods. And then we compare our models to the previous state of art on ImgNet classification. The previous state of art model is released by Facebook, where they train the models on billions of Instagram images with weak labels. And by comparing our methods, which is the first row here, you can see in terms of parameters, we're 10 times less. And in terms of actual data, because we're only trained on ImgNet, while the second model trained on billions of Instagram images. So we're 3,000 times less trained data. But in terms of accuracy, we're even 0.1 better, which demonstrates the power and the effectiveness of our proposed method. So after this work, we also do some follow-ups. The first follow-up is using this adversarial propagation to improve object detection. And this paper is accepted at CVPR 2021. However, the motivation here is a little bit different. We all know that for the object detection, we need to first go through our pre-train and then fine-tuning learning paradigm, right? And by following this learning paradigm here, we note that fine-tuning different pre-trained models usually will yield very similar performance on both accuracy and robustness. So here, D2 and D5 are the detection version of EfficientNet. And you can see these three different colors indicate the models are either vanilla trained or pre-trained on the ADU prop or pre-trained with noisy students. You can see that even though like for pre-trained models, they have different powers. I think in the original pre-trained model, in terms of the ImgNet results, they at least get 1 or 2% percentage performance difference. But when fine-tuning on the detection sets, you can see basically like there yields very close performance on the original, on the COCO detection result, for both D2 and D5. And also we do a generalization test on the COCO-C dataset, which is a cropped version of a COCO dataset for benchmarking the robustness. And we can see again, like the robustness here is pretty same. So that means the advantage brought by your upstream classification task usually cannot transfer well to the downstream task for accuracy and robustness. So given this observation, what we want to do is that we want to directly augmenting the downstream object detection task. And by making some non-trivial modifications, we can successfully apply the adversarial propagation to the object detection case, and the results basically look like this. So firstly, we can achieve considerable improvements on both clean accuracy and robustness. The detection ADU prop consistently improve models of various scales, and the performance gain is especially notable for large scale detectors with high capacity. And also our models methods generalize pretty well to the single class detection task, such as the face and the pedestrian detection. And we further evaluate the robustness of the detector trained by our DET ADU prop and the virus corruption on COCO-C, which spans 15 corruptions and 5 severity level. detection ADV prop can achieve even more significant improvements on these distorted images than on the clean images over the baseline. And the performance gain also tend to become, like say, larger when the corruption strength is stronger. So that's a pretty good news, right? Another manifest of the model robustness is whether it can return strong performance against domain shift. So what we do next is that we use these trained detectors to run inference directly on the VOC dataset, which has different data distribution from the COCO. And as shown in this table, you can see DET ADV prop always outperforms the vanilla baseline and the auto-aug training baseline, and for all the model scales and every evaluation metric. So if you want to know more about this work, you're welcome to our CPR poster on June 25th from 6 a.m. to 8:30 a.m. I think it's Eastern time. And another follow-up is the shape texture device training. So at native to use adversarial examples to improve your image recognition, what we can do is that we can use Q-conflict images. So the texture shape Q-conflict images is first introduced in the well-known image training CNNs are biased towards texture paper. What they do there is you take a texture pattern images and take a original natural images. You just apply the GAN to make sure their texture pattern and the shape pattern and create this new one. And for this new images, you can see you get the shape of cat, but for texture of elephants. So the original purpose of this shape texture Q-conflict images is to validate whether like your networks are biased towards the shape or the texture. But what we do here is a little bit different. Let's go over like the training pipeline. The first is that you can first randomly sample 2 images from your training data set. For example, you can get a chimpanzee images and the lemon images. And then you can apply the GAN to make sure there's their texture pattern and the shape pattern. So given these images, you get 3 possibilities to train your models, right? The first is that you think this is a chimpanzee image. So, and the label assignment is say, okay, this image is a chimpanzee and you need to learn this correlationships. And by doing so, this will result a shape bias model because for this image, the chimpanzee only represents the shape information. But also you can also say like, this is a lemon. But again, this will result a texture bias model because the lemon here only provides the texture pattern. And what we do here is it's very simple. What we do here is just say, okay, this image is a chimpanzee and also a lemon. So it's a soft assignment of labels. And this can result in our shape texture debiased models. And here's the empirical results. You can see compared to the original baseline here, you get a huge improvement of, for example, on the original image classification, and also on the auto generalization, say image A dataset, C dataset, stylized dataset, and also be more robust against FGSM attack. And also, what we didn't show here is that we conduct some additional experiments to verify that our models indeed learn some much better shape and texture cues compared to other baseline models. Okay, takeaways. So the first takeaway message is that adversarial learned features are indeed valuable. Previous work has provided some qualitative evidence to show adversarial images bring some new features, and these new features seems pretty good. And what we do here is we provide the first quantitative result to show that by getting these robust features, you indeed can get better image recognition models on both the classification, detection, and also the segmentation tasks. The second takeaway message is that adversarial examples can actually serve as a pretty general data augmentation method to improve your model. For example, like the image flipping is a very popular way to augment your image trained data, right? But flipping does not make too much sense for the NLP task or for the reinforcement learning task. But adversarial examples are very different. You can find an adversarial example for image recognition, and also for NLP, and also for reinforcement learning. So it's very possible that you can just use adversarial examples to build a universal data augmentation method to improve your deep learning algorithm, regardless like what is the task for this deep learning model. The third point is that disentangled learning is pretty important when inputs came from different distributions. And what we do here is that we apply separate personalization to make sure like each models, like each module, say adversarial and clean, their features can be correctly learned by the models. So that's a pretty important point. And just to summarize, what we do here is that we use adversarial prop, and this is a CPR 2020 paper. We show that adversarial perturbations can help the classification task. And also in this year's CPR, we show that it can help the detection algorithm. And also in our ICLR 2021 paper, we show that other than use adversarial perturbation, we can use those shift texture Q conflict images to improve your model on classification and segmentation. And also we have some ongoing projects trying to see, okay, whether you can use the synthetic data or the uncurated internet data to improve your models further. And also maybe some possibility like for different tasks, like the future learning, unsupervised, semi-supervised learning, and the multimodality learning to just use this like adversarial data to improve them in general. So lastly, I want to thank my amazing collaborators for their great help for this project. And also I want to thank Facebook for providing me the Facebook fellowship and also the Open Fair for the funding my lab. Lastly, I want to do a small advertisement here. In our lab at UCSC, we still have multiple positions for remote summer interns and within students. So if you're interested, you can just send me an email. And that's all. I'm happy to take questions here.
Thanks, Cihang, for the great talk. So we have some questions from the audience. The first question is from Zhengyu Zhao. The question is that it makes sense that fine-tuning on clean images improves the accuracy of adversarially trained model on clean images, but will it harm the robust accuracy, which is the accuracy of adversarial images?
Yeah, that's a good question, and that's a correct point. So in terms of, say, you fine-tune our adversarial trained models on the clean images, it indeed, like say, you get less adversarial robustness. But as shown in this paper, we find the benefits is really like desired for many applications. For example, you not only say want your higher imagenet accuracy, but also you want your higher accuracy on a lot of auto distribution samples, right? Like the ImageC dataset, ImageA dataset, which are more, maybe they are more real data in the real world. And so even by say sacrificing your adversarial robustness a little bit, but for trading for this strong generalization and the in-domain generalizations, I think that's a good and a promising direction to go further. But of course, ideally, we would definitely want to get a one method to say, okay, you not only say strong robustness, but also say strong in-domain or the out-of-domain generalization. But I think we still need a lot of efforts to make it be real.
Yeah, thanks for the answer. And the follow-up question is that will solely using adversarial training without your adversarial pop technique improve out of distribution accuracy?
Well, I do not have a very rigorous proof for this, but previously I do have tested the adversarial trained models on the auto distribution data like the ImageSC dataset. I found that if your model tend to be robust, say adversarial robust, it will hurt a little bit on the auto distribution dataset like the ImageSC. But I do not do this very seriously, and only what I have done is for ImageSC dataset. So I'm not sure, but from the ImageSC result, it indeed seems that it will hurt the out of distribution generalization ability. Yeah.
Yeah. Cool. Thanks for your answers. So let's move